Geologic history. We're going to take a look at the relative dating of rock layers and how we learn about the Earth's history by studying sedimentary rocks. To get started, we need to look at something called absolute dating. Now, absolute dating of rocks involves the use of a method known as radioactive dating, carbon dating, radioactive decay. This allows us to figure out the actual age of a rock or a fossil, an actual numeric age. For example, if I were to say this trilobite fossil is 489 million years old, that's an example of absolute dating because I'm using a specific number. Now, there's another type of dating that we use when we're looking at the history of the Earth, and that's called relative dating. Now, this would be figuring out simply which rock or fossil or geologic event came first, which one came second, third, etc., without using any specific quantitative values. For example, if I were to say the trilobite fossil is older than the dinosaur tooth fossil, that would be an example of relative dating, because I'm not using any numbers, I'm doing a comparison. Let me give you one more example of the difference between absolute and relative dating. Let's take a look at these two cars here. What if I were to make a statement like the red car cost $90,000 and the silver car cost $15,000? Now, because I'm using specific numbers, this is an example of using an absolute comparison. On the other hand, I could make a statement like the red car is more expensive than the silver car. Now, because I'm not using any specifics, I'm simply doing a comparison. This would be an example of a relative comparison. What about in terms of rock layers? Well, here I have some layers of sandstone out in the American Southwest. If I were to say something like, this layer of rock is 225 million years old, that's an absolute dating statement because I have a number, I'm being specific. But if I were to say, this layer of sandstone is older than this layer, that would be an example of relative dating. Now, of course, in the study of Earth's history, we're going to use both absolute dating through radioactive decay, and we're going to use relative dating through geologic sequencing. And that's what I want to focus on today. So let's get into this a little bit. And before we get too deep, though, we have to start with one underlying principle, an assumption, if you will. And it has a name. It's called the law of uniformitarianism. Yes, that's a 9-syllable word. Well, what this law essentially says is that all of the things that we observe happening on Earth today, including weather, storms, and wind, erosion and deposition by rivers and by glaciers, geologic events and tectonic events like earthquakes and volcanic eruptions and the motion of the plates, all of these processes that we see happening today, well, the law of uniformitarianism says that we can assume that they happened the same way in the past. And that's an important assumption because it allows us to look at rock layers from millions of years ago and have a good idea as to what actually happened to form those rock layers, because we're seeing the same types of things happening today. Now, one of the great tools we're going to use in studying the history of the Earth, is something called a road cut. And you see a road cut here. I'm sure you've seen it before. This is where rocks, mountains are cut away by dynamite so that highways and roads could be built. Now, what's great about a road cut is it allows us to see further back in time as you go deeper down. You can see different layers of rock which were deposited further and further in the past. And based on what the evidence is, you can get an idea of what the geologic history of the area was like. So we're going to be taking a look at a lot of these sorts of outcrops, escarpments, cliffs, and exposed bedrock to figure out what the history of the Earth has included. Generally, though, we're not going to look at actual photographs. We're going to look at cross-sections, geologic cross-sections, or diagrams like this one here. This is a diagram representing an outcrop of rock. And so we see a bunch of layers of sedimentary rock, and we see an igneous intrusion, and we see a fault, and some weathering, and all sorts of stuff. And so our job is going to be to analyze these sorts of diagrams. And the first thing we need to be able to do is to identify what each layer is made of. Fortunately, if we look at our copy of the New York State Earth Science Reference Tables, and we look at these sedimentary and metamorphic rock charts, we will see these symbols. They're called map symbols. each of the sedimentary rocks has its own unique symbol that will be used in these geologic diagrams. Of course, the same is true for our metamorphic rocks. You'll notice slate, phyllite, gneiss, marble, etc. They all have their own unique symbols. And this is what we're looking at when we look at these cross-sections. So, for example, in this particular diagram, I know that this layer is made of sandstone, and this is limestone, some conglomerate here, and some shale, and some siltstone. And I can tell that by looking at the symbols used in the diagram. Now, ultimately, our goal is this. I want to be able to look at this picture and figure out what event happened first, second, third, fourth. Ultimately, how did this structure form? And by doing so, I'm getting some insight into the geologic history of this region. And so to start, we need to look at some underlying important rules that apply when studying the history of the Earth. So let's get started with rule number 1. And here's what this rule says. It says that sedimentary rocks tend to form, not always, but they tend to form when sediments are deposited in the bottom of a body of water, specifically the ocean. Let's take a look at a little animation here. What you'll see is a body of water, and you notice sand and silt and clay and pebbles, cobbles, and even boulders slowly are deposited on the bottom of the ocean. And then over many thousands and millions of years, these sediments are compressed by the weight of the water into layers of sedimentary rock, seen here. So let's keep in mind that when we see sedimentary rock layers, we know that at one point they were likely underwater. Rule number 2. If rocks are weathered and eroded, then they must have been, at least for a period of time, out of the water. And this is because weathering and erosion of rock layers mainly happens on the surface of the Earth, not underwater. Let's go back to that same animation again. Now we're underwater, sediments are deposited, compressed into sedimentary rocks, and then some event will happen. In this case, we'll see some folding, and that causes the layers to be what we call uplifted out of the water, where wind and rain and snow and ice can wear them away, and we see weathering and erosion taking place. So again, the layers themselves tend to form underwater. The weathering and erosion happens above the water. Let's keep that in mind. Rule number 3, and this one's pretty logical. When we look at layers of rock, we are allowed to make this assumption, and that is that the layers of rock towards the bottom of the sequence are going to be the oldest. And as you get closer to the top, they're going to get younger and younger. And this is called the law of superposition. And this is going to be true in almost all cases. The exception would be if the layers of rock have been so severely deformed, so folded that they've actually been flipped upside down. It's called overturning, and this does happen sometimes. For the sequences we're going to start with, though, we can assume that the layers have not been overturned and that the law of superposition applies. So let's take a look at an actual sequence of layers here, and let's figure out what events happen to form this sequence. So again, the law of superposition says that the layers on the bottom, like this layer, layer D, which happens to be siltstone, must have been deposited first. And then above it, layer C, then B, and then A. And so I know the sequence in which my layers of rock formed. But there's one other, or actually a couple other things that have taken place here. You'll notice that the surface of these rocks is all irregular and jagged, and we even see some trees. Well, that means that we can no longer be underwater, and that there had to be a period of uplift followed by weathering and erosion, which is actually still taking place today at this particular sequence. Now that's a very basic sequence. Let's add some more rules and get a little bit more complex. Rule number 4. Sedimentary layers are generally deposited horizontally or flat. And they're only going to be messed up if some sort of deformation has taken place. Things like folding of the layers, faulting or cracking of the layers, or even tilting of the layers. Now this idea that the layers form originally in a horizontal manner has a name, and it's called the law of original horizontality. Keeping this rule in mind, let's take a look at another animation here. So we're seeing these layers form. Notice how they're all flat and horizontal. It's not until some sort of deformation, in this case folding, takes place, that the layers lose their horizontal nature. Let's do a sequence. Here are some layers of rock that have clearly been deformed. So let's go ahead and do the entire sequence. Now the first thing to be deposited, again, according to the law of superposition, would be whatever's on the bottom. In this case, it's this layer of shale. Above that would be our sandstone, limestone, more shale, more limestone, and then this top layer of sandstone, some of which is missing. Now I know that all these layers had to be deposited horizontally first, and then at some point later on, there was some deformation. In this case, because the layers are folded, we're going to call it simply folding. Now there's a couple more things to think about though. You'll notice how the top of this sequence, some of that top sandstone layer is missing. And I'm going to infer that the folding caused a period of uplift which allowed that sandstone to be weathered and eroded. And that explains why some of it is missing. And so there's a nice complete sequence of events. Let's take a look at some different types of deformation. Here's another sequence. Looking at the events, I want you to notice something. It's a little tricky to tell which layers match up because we have this large fault going through the middle. And so I have to stop and identify what layers on the left might match up with which layers on the right. So I'll notice, you see this layer of shale and above it sandstone and limestone. I think it's safe to assume that that would be the same as this shale, above it sandstone, and above it limestone. Now that in mind, this means that this limestone over here is actually the oldest. I don't see it on the right-hand side because it's not in my particular view here, but I can safely infer that that was the first one there. And then, of course, followed by this shale, which is the same as this one, and then this sandstone, which is the same as this one, limestone, and then sandstone and sandstone. So we've accounted for all our layers. But what about the next process? And you will notice that these layers appear to have been tilted. And you'll notice I include step 6, tilting. All that means is that originally they were flat and horizontal, like this blue line, but something has taken place, likely associated with the movement of Earth's plates. That movement has caused tilting. Probably at the same time as the tilting, this crack formed, which is faulting. So I'm going to include tilting and faulting together. It's very difficult to tell which one came first, so I'll just include them as step number 6. And at the same time, if you look at the surface, it looks like there's been some weathering and erosion. So I can also infer that the tilting and the faulting of the layers caused a period of uplift, which allowed for weathering and erosion. And there's a complete sequence. But we have more rules to consider. For example, rule number 4 involves intrusions, and it says that an igneous intrusion will always be younger than the rock that it affects, or the rock that it metamorphoses. So let's take a look at this sequence right here. Now what you notice is this area right here, and what this is an igneous intrusion. That means that at some point in history, magma, melted rock, molten hot rock, forced its way up through some of the layers, and then solidified into solid igneous rock. Layer C is completely igneous. Along the way, though, that hot magma burned the layers that it passed through and caused what we call contact metamorphism. And we'll come back to that in just a minute. Let's try and figure out our sequence first. Law of superposition says layer E, the limestone, would be first, and then D, the shale, would be second. Being that the intrusion is right above the shale and it has affected the shale, I know that the intrusion probably came next. And with the intrusion, I have all of these whiskers, as I call them, which represents contact metamorphism. Once the intrusion solidified into solid igneous rock, we had additional deposition of layers B, sandstone, and A, conglomerate. I don't see any evidence of weathering and erosion, and so that right there is a complete sequence. But let's talk about this intrusion a little bit more. Remember, this is hot magma, and so when it touches any other layers, it's going to burn it or metamorphosize it. And so you see these little whiskers right here shown in purple. That is an area where the hot magma actually burned this limestone and shale that was already existing. And so one of the common questions we're going to ask ourselves is, well, what rock would form right in that purple zone? For example, where I put this X. And it's actually easy enough to figure out if I have my copy of the reference tables. So I know that just below point X, I used to have shale, and I know that by the symbol. But once we take our shale and we touch it with magma, when the shale comes into contact with magma, it's going to be burned or changed. And in this case, I'm looking for something that forms from the contact metamorphism. And my best argument in this case would probably be hornfels. And so I know that the rock found at location X would be the metamorphic rock hornfels. Now that's a little bit confusing, so let's look at another example. Here's another cross-section with yet another intrusion. And so let's do our sequence. First, I'm going to have the deposition of layer A, followed by B directly above it. And then in this case, I actually think layer D came next. And then the intrusion and metamorphism, followed by uplift and some weathering and erosion. Now let me explain why I think this is. Actually, before we explain why, let's take a look at another point here. Let's say we have point Y. What do I know the rock is at point Y? Well, if I again look at my reference tables, that used to be sandstone. But it was then touched by this hot magma, and the sandstone was metamorphosed. And when I take sandstone and I touch it with magma, it will metamorphosize into quartzite, seen on the metamorphic rock chart here. But as I said, let's talk about this a little bit more. How did I know that this layer, D, the shale, was there before the intrusion labeled C? Well, I do know that D is going to be the older layer, and the reason I know is because D was metamorphosed by the intrusion. Layer D was actually affected by this magma, and if layer D was burned by the magma, it had to be there first. Think about it logically. You cannot metamorphosize a rock if that rock doesn't exist yet. So D had to be deposited, and then sometime later on, intrusion C came along. You know what? Let's revisit that previous sequence that we did before. How was it that I knew that B came after C? I know that C is older, but how do I know? Well, in this case, layer B was not metamorphosized. You see, there are no whiskers in layer B. So had B been there, it would have been burned. It would have been metamorphosed. But because it wasn't, it had to come after the intrusion came in and solidified. So these little whiskers, as I call them, are very, very important in determining your sequence. If a layer was affected by intrusion, it was there first. If it wasn't, it must have come after. We have a couple more rules to look at. Rule number 5 involves faults. Now, faults are cracks that occur when you have major tectonic movements, specifically earthquakes. And we know that if we have a fault, it has to have come after, or it has to be younger than whatever rocks that it cuts through. Let's look at this example again. Now, if we're doing a fault, you see it cutting through right there. That crack that I highlighted in red here, that is our fault in question. But this one's tricky because we also have an intrusion. We have some uplift and weathering and erosion. There's a lot going on here. So let's go ahead and do our sequence. Now, first, I think we had deposition of this limestone, and then the shale, which is, of course, the same as this shale over here. Then, following the law of superposition, oldest is on the bottom, I have sandstone above it, which is the same as this one, and then conglomerate, which is the same as this one. Of course, we have this layer of limestone and this one, which are the same, and then the final layer, which is this siltstone. Now, the big question is, did the fault happen next, or did the intrusion happen next? And the way I can tell is that the intrusion was not faulted. You'll notice how there's no crack in the intrusion. Well, that means that the fault had to come first. So I have this fault right here coming next, followed by probably the uplift and weathering and erosion seen on the surface. Because remember, faulting is a kind of deformation. It probably caused the land to uplift. And then at some point later on, we had our intrusion and our contact metamorphism. That's a tricky one. There's a lot going on there. Let's look at a couple more rules. Here's number 6. We know that when we get uplift of layers and they're weathered and eroded and then they subside or sink back down and get buried, we're going to get the formation of something called an unconformity. unconformities are incredibly important in the study of geologic history because they represent a missing part of the story, a missing part of the rock record. In other words, a geologic mystery. It's kind of like if I took a book that you were reading and I ripped out 50 pages in the middle of the book. Well, you would know exactly what happened at the beginning of the story, and you'd know what happened at the end, but the middle would be a mystery. Now let me show you what an unconformity looks like and how it forms. We're going to go back to our animation, and we have horizontal layers forming underwater, and this is from deposition, and then they're going to be uplifted and deformed, and when they're uplifted out of the water, they get eroded and weathered, and so stuff is taken away. But then they sink back under the water and new layers form on top of that weathered surface. And so we have a problem here, and that is I know what happened at the beginning and I know what happened at the middle, but the layers in the middle are gone. They were weathered away, and that's what an unconformity is. It's a missing piece of the puzzle. Now let me show you how this would work in a sequence. Here's a sequence. No faults, no intrusions, but we do have some other stuff happening here that's a little tricky. So again, let's follow the law of superposition. Layer G, the sandstone, was deposited, then the conglomerate, the shale, the limestone, which is not just here at point D, it's also the same as point H. That's the same layer. And then above that, the shale, layer C. Now, you'll notice those layers on the bottom are messed up. They've been deformed, and it appears to me that it was a period of folding. Likely, that folding caused the formation of this line right here. That is my unconformity. And so how did we get that? Well, when folding happens, it often causes uplift. And we know that when layers are lifted up out of the water, they can be weathered and eroded. That's what gives us this kind of missing part of my folds here, this top part that's been chopped off. Now, at the moment, it's not an unconformity. Something else has to happen, and that is those bottom layers have to subside. We have to have subsidence, and they have to sink back underwater so that layer B, the limestone, can form on top. Above B was A, the shale, and then it looks like there was another period of uplift and weathering and erosion, and I can tell because of this yellow weathered surface on top. So I have uplift and weathering and erosion. But because this top layer is not buried, there was no subsidence. And that means the yellow is not an unconformity. In order to be an unconformity, it needs to be a buried, eroded surface. So, if I see an unconformity in my sequence, I know that I had to have a period of uplift, weathering and erosion, and subsidence. Those three steps together are what creates the unconformity. So you see here in red, this layer right here, this not even a layer, this boundary is an unconformity. And it's important because we know exactly what happened down here, right? I see the layers, I see the folding, I know exactly what happened. I also know what happened up here. I see the layers, I see the weathering, I know the story. But if I'm a geologist and I see this red boundary, that is a mystery. The unconformity represents a period of time where we don't know what was going on. We don't know any of the details of the geologic history. And this is one of the biggest mysteries in geologic history and studying the history of the Earth. Let's do one more rule, and this is called the law of inclusions. And what it states is that any inclusions, and that would be little chunks of another rock layer, if they're included in that rock layer, then they must have been around first. Inclusions must be older than the layer they're in. And again, this is called the law of inclusions. And the best way to think of this law is to look at a rock like this sedimentary rock called conglomerate. Now, conglomerate is made of all sorts of sediments, big and small, including pebbles and maybe even cobbles and boulders. Well, what I know is that the pebbles that make up the conglomerate must have been around before the conglomerate itself was around. Think about it like baking a cake. You had to have the eggs and the flour before you had the cake itself. In this example, I had to have the pebbles before I had the conglomerate because they make up the conglomerate. Now, before we finish, let's take a look at one last tricky sequence here, and let's try and do a sequence of events together. This is a particularly tough one, but if we take it slow and follow our rules, it shouldn't be too bad. Now, I'm going to start by looking at my lowest layers. Now I see A, B, and C here. These are all intrusions, and they have all metamorphosed other layers, which means they couldn't have been there first. The other layers that they affected had to be there first. So I'm going to start with my lowest sedimentary layer, which is layer G, this limestone right here. I also see this layer right above it, layer F. That probably came next, but these two layers have been deformed. There has been tilting, and there's also been this faulting that has taken place here. Okay, now after the faulting, I think we got our first intrusion, intrusion A, along with some contact metamorphism. After A comes B with contact metamorphism, and then those layers, G, F, A, and B, were all uplifted and weathered and eroded, creating this unconformity, which we see right here. Now I know that it's an unconformity because it's got another layer on top, so we had to have some subsidence. Back underwater, layer D was deposited, sandstone. Above D, we dropped off E and then H. And so now I've accounted for all my layers. I need to think about what might be next. I do have to deal with intrusion C, but I also see that there was some weathering and erosion. And I think that probably came later on. So let's go with intrusion C and contact metamorphism. And then the final thing was that all of this was uplifted out of the water where weathering and erosion took place. I know that that weathering and erosion was last because if you look at intrusion C, part of it has been eroded. That's a pretty tricky sequence. But again, if we follow our rules of relative dating, then it's not too hard to figure out. Hope this video was helpful.